Today we are taking a break from calculus and we are introducing a new notation called sigma notation. And basically it's a way to write a huge sum of terms, right? So if we're just going to add up all of these terms, basically, then we can just say, okay, well, we're going to add we're just going to, this symbol here, we call it sigma, means we're going to sum up all of these. And then this AI, so basically I starts with 1, so that's why basically the 1 goes in for I here, and I get A1. And then I are integers until I get up to here. So basically I would add A1, then the next I would be 2, A2 plus A3 plus A4, until I got to the last term, which is the top number here, which is N. So basically this is my starting number that I put in for I, and this is my last number. So they don't have to start with 1. And for the index, so this is called the index, the I. So a lot of times I is used, sometimes J is used, sometimes K is used. It doesn't matter, they're interchangeable. This is your starting number, so I here should match I here. If it's J here, it should make J here. If it's mixed up, it's probably because I mixed them up accidentally. Okay. So basically AI is the ith term of the sum, right? So basically if I wanted like A7 would be the 7th term in the sum. It would be 1, 2, 3, 4, and then I 5, 6, 7. So it would just be the 7th term. It wouldn't be the sum. It would just be the term. And this symbol means we're going to add them all up. So my upper bound is on top, right, up here, and my lower bound is here. That's why we call it. The lower bound is 1, so they can be different, okay? So let's just use this. It's just a little bit easier, to just kind of use it and see how it works. So I have I starting at 1 up until 5, and I have just plain I. So the I, or whatever it is, if it's J or K, is where I put these numbers, and they're always integers. So this essentially means 1, I start with I as 1, and I put it in for I, and then I keep going with my integers, plus 2, plus 3, plus 4, until I get to my top number, plus 5. So this, right, is another way for writing this. Now, that might seem kind of like, oh, well, there's only 5 terms there. But if I had 100, if I had the sum of 1 plus up to 100, that's a lot of things to write out, right? So it would be easier for me to write it as I goes to is 1, 2, and then I put my 100 on top for I. So if I wanted to go out to 100, like I've just written the first 5 terms, but I could actually add these. So this would be, let's see, this is 5, and this is 5, so I have 15. But we have some formulas to make that a little bit easier that we're going to get to in a moment. I'm just trying to get you used to the notation for right now. Okay, so this time I have I squared, I starting with 3 and ending with 7. I really didn't need the I on top, but so basically this means I'm going to start with 3, so I'm going to 3 squared plus 4 squared plus 5 squared plus 7 squared. I stop with the top number. So that's what this means, right, is the sum of these. I'm not going to add them up. You can use a calculator and add them up if you really want to. But this is what it represents, is the sum of these terms. Okay? So let me just write out one more. We're going to get really used to this one in a little bit. So I just want to write out some terms here, right? So this is summation formula, and this means I'm going to plug in starting with 1 up until I get to the nth term. So the only place, I look in here, the only place where I have the I is this, right? So these will be f of x sub 1 times delta x, that's I plugged in the 1, and then plus f of x sub 2 times delta x, and then a third one would be f of x sub 3 times delta x, and these would go on and on and on until I got to my last term, which is f of x sub n times delta x, because that would be my last term. I can't write out n terms because I don't know what n is, so I just write out a few showing the pattern, and then I end with the last term. So if I plugged in n here, I would get f sub x sub n, and then times delta x. Okay, so it's just a way to write a sum, that's all, especially when they get more complicated. All right, so let's look at this one. So this time we're given some stuff, and we want to write it in summation form. Okay. Now there's a couple of different ways. Like there's no super hard and fast way to do this. You know, I can either I notice I'm starting with 4, right? So like the easy one to do is, oh, these are all raised to the 6th power. So I have I to the 6th, and then I'm starting with I equals 4, and then I end with 9 on top. That's perfectly legitimate. I could, if I really wanted to, like if I thought of this as the first term, the second term, the third term, the fourth term, the fifth term, and the sixth term, then I could really say that each one of these would be I plus 3 to the 6th, right? So another way to do it would be I plus 3 all raised to the 6th, and that would be starting with I equals 1. Because when I plug in 1 here, I will get 4 to the 6th, right? And so the last one would just be to, I think it would be 6, right? Because when I plugged in 6, I would get 9 to the 6th. So both of these are completely equivalent. This is obviously the easier one to write, but this is also equivalent. I mean, I could actually start it at 2. I can start it wherever, as long as my formula works, right? As long as when I put in this number, I get the first one, okay? All right. So let's look at the second one. Let's write this one out as a sum. Okay, so let's see. So I want to think of this as, let's see, how do I want to write this one? All right, so I notice that my first one is 2 squared, 3 squared, 4 squared, 5 squared, and these second ones are the same number. So I think I could do, basically, if I start with I equals 2, then this would be I squared plus I. And I could end, my last term would be 5. And if I plug in I here, I get 2 squared plus 2. I plug in the next one, I get 3 squared plus 3. Okay. Again, I could start at 1, and then I could say I plus 1, right? The same thing, equivalent expression would be, if I started at 1, then this would be I plus 1 squared plus I plus 1, right? Because then when I plugged in 2, or 1 here, I'd get, actually, let me make that a real I there. I'd get 2 squared plus 2, and so forth and so on. And then I would have to end it at 4. I mean, I still have the same, right? The difference between 5 and 2 is 3, and the difference between 4 and 1 is 3, right? So I still have the same number of terms. I actually have one more term than that because I actually use, right, the ends. But I get the same amount of terms and the same number. All right, so let's do one more of these. All right, so this time, all right, I could write this. All right, so I notice that my front terms are all 2 to a power. Right, so I have basically 2 to a power, and then the 2 stays constant at the back. So this is 2. So I am going to make a choice and say I'm going to start with, I'll say 2 to the I, right? And I can just start because my very first one starts with 2. I can say that I is 2. And then I know my last term out here is n, so I would go to the nth power. Or, I'm sorry, to the nth term. Okay? So the only thing that's changing in all of these is the exponent up here. So that's where the, that's where my index goes, whether I use I, j, k, whatever. And then I have this. Okay? All right, so some properties of sigma notation. Right? One that we could have used right up above here is that if I have the sum of A plus B, then I could write this as separate sums, right? Now in this case, this is more like the previous one, where they both changed, right? So this one was I squared plus I, right? So I could have written it, so we had, the one that we had, we called I squared plus I, and we started with I equals 1 to 5, or actually, we called it 2 to 5, okay. And so we could have written this as two separate ones, as I squared from 2 to 5 plus I from I equals 2 to 5. So that means we can separate them. Now, why do we want to do that? Well, not for small numbers, it's really not a big deal because if I plug in 2, 3, 4, and 5, I can just add them all up. But when I'm going to add up great sums of them, I actually have formulas for these. So it's kind of a nice way to break it up and use separate formulas. Okay. Oh, the other one. Sorry, I only talked about the one. This is basically the constant multiplier rule. It's just like with the derivative, right? If you have a constant times something, then you can put the constant kind of on the outside. So basically the c can just get multiplied by the end rather than, right? So for instance, if I had, right, so if I had like 2 times I, like this, from I equals 1 to 6, right? My terms, I could write them as 2 times 1 plus 2 times 2 plus 2 times 3, and so forth. Or, essentially, I could factor out the 2, put the 2 on the outside like this, right, until I get up to my last term here. I should finish it. It would be 2 to the 6th, and then I have I is 1 to 6, and then I would just have the I here. So in the end, I could just do, this would be just 2 times 1 plus 2 plus 3 out here until I put the plus 6. I'm getting lazy with writing all my, there's not that many numbers, but you know what I mean. Okay, so that's another way to write it. So when I have a constant here, I can just sort of pull it out in front and multiply it through the, I can just add these numbers up and then multiply by 2 at the end. Okay. All right, so that's a couple of basic properties. All right, so some that are actually some that we can use to sum things, right? So now, you know, if we're just having, if we just have a couple of terms and we write it like this, then it's not a big deal. We can add them up. But if we have like, if I have basically a whole bunch of terms and I want to add them up, it's nice to have a formula for this. Now, what this means is basically this is the sum of a constant. So this would be like k is a constant, and of course n has to be bigger than this. That's bigger than or equal to this. So this would be an example, like would be I equals 1 to 20, and then I have basically 2, right? So 2 is a constant. So essentially there's no place for me to put my I. So essentially this really means like I have 2 plus 2 plus 2 plus 2. And this is like the first, the second, the third, the fourth. And so basically I have 20, right, 2's that I'm going to add up. So what this basically says is that this just means, essentially, I'm going to have this many of these constants. So I can just say that, okay, well then this is 2 times 20. So I just end up with 40. And if I add up 22's, I will in fact get 40. So this is our first way to sum something. Now, this is the most basic example. Now what I find is actually often students, because this one doesn't have an I in it, that they forget this part. But the reason that this is, right, is because I'm going to have 20 of these. This means there isn't a place to put my I, so they're all going to be 2's, but I'm still going to have the first, the second, the third, the fourth, out until the 20th. So basically I have 2's added together 20 times, which is 2 times 20, which is 40. Okay? All right, so like just to do one more of those, if I have I equals 1 to 100 of, I don't know, we'll do 4, right? Then this means that I'm going to have 100, I'm going to add 4 together 100 times, which is really just 4 times 100, which is 400. Isn't that lovely? Now, an easy one to kind of forget is if I have I equals 1 to, I don't know, 300, and I just have a 1 here, right? So I'm still going to have 100 ones that I'm going to add. So I would add 1 plus 1 plus 1 until I get to 100, and my formula says, well, I don't need to do all of that. I just have 300 ones, so that means I have 300 times 1, which is 300. Okay, so this is our first useful information or bits of how we can add these up. Because why write them all neat and nice if I can't actually use it to make my life easier? I mean, I do like to write things like without writing them over and over, but it's always good to be useful. All right, so here is my second formula. So if I just have plain I, right, and I'm adding it, so every time I go up by 1, so 1 plus 2 plus 3 plus blah, 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 until I get to my n, then there's a formula for that. So that would, to sum it up, like to actually sum it up. So the other one I just multiplied with, when I have a constant, I just have basically that constant number times the number of times it is. In this time, right, somebody sweated and figured this one out. When I have 1 plus 2 plus 3 plus 4 plus whatever until I get to the last number, this ends up being n times n plus 1 over 2. Okay, like I did the 1, right? I showed you that I equals 1 to 5, that one. Remember I said that that was 1 plus 2 plus 3 plus 4 out to 5, and that was 15. If I try to, let me use my formula here. Okay, so now if I have I equals 1 to 5 of I know that this is my formula. Now my n here is 5 on top, so that would be 5 times 6 over 2, which is in fact 15. Now we really added these, right, on the earlier in the lecture, and we found that. But now I can use this formula and be like, oh, that's awesome, right? So like 5 is easy, I could have just added it up. But what if I have I equals 1 to, let's see, oops, I don't know why I did that. Let's say 100, and I have I. Okay, so this means using my formula up here. Now, you're not going to have to memorize this formula. I will at least give you this. I might, so this is the same thing. It's just multiplied through and then broken apart over things. It depends on what I'm using it for. Like for just like summing it up right now, this is a really nice, useful formula. For later on, when we start taking limits of things, this is going to be sort of the more useful way. So you can use them interchangeably at this point. Okay, so if I want to sum up I equals 100, I know that that formula, right, up here is n times n plus 1 over 2. So that means I have 100 times 101 over 2, which means really this is 50 times 101, whatever that is. You can get out your calculator and figure it out. Okay, but that is the sum. So it's a really easy multiplication. All right, so what happens if I don't start at 1? Okay, so what if I had the sum of 5, if I start, let me use j this time, j is 5 to 20, okay? So what I can do, okay, this is the same, right? So I just want to start with 5 and go up to 20, but that's so many numbers, I don't want to add them. So I can actually use my formula, okay? So think of it this way. So I can do this. So if I want to, all my formulas, they start with I as 1. So I'm going to do j equals 1 to 20 of I. Now that's not the same thing, right? Because I'm going to have these extra first 5 terms in here, but I can subtract them. So basically this will sum up 1 to 20, and then if I sum up 1 to 5 and subtract it, I will get the right thing. So if I start this one from j is 1 to 5, then I can do that as well. Okay, so let's just put some numbers on that, right? So remember our formula for summation was n times n plus 1 over 2, right? So if I do this one, this is going to give me, putting in my n on top, for just this first one will be n, actually I can replace n, 20 times 21 over 2, and then I'm going to have minus 5 times 6 over 2. Now, we already said this one was 15, so then this one is 10 times 21, which is 210, so then 210 minus 15, there is 195. There, I summed it up. And I didn't have to do 1 plus 2 plus, or I 5 plus 6 plus 7 plus 8. All right, so just some ways to use them. All right, so we also have them for when they're squared, right? So if I wanted to add up, I have j is 1 to, I don't know, 100 here, right, of j squared. then that would be this, right? 1 plus 1 squared plus 2 squared plus 3 squared all the way out to 100 squared. Unfortunately for us, we don't have to add those all up because we can use this formula here, right? So my n is 100, so this would be, my sum would be 100 times 101 times 2 times 100, which is 201, plus 1 over 6. All right, now I'm not going to sum that all up, but I know you can do the multiplication. So we just multiply those all together on top and divide by 6. Easy peasy. All right. So we can do, so what if I combine them? Right. So what if I have, we'll use k is 1 to 20 of I squared plus I. So my formulas say that I can do, oops, I used k and I. Let's see, I told you that's because I forget to write the right thing. I think I'm being nice or interesting by changing them up, but then I mix them up. So we're going to have k squared plus k, so I can break this apart into 2 separate ones as k squared and then plus k from 20 to k is 1. So now I can use my 2 separate formulas, right? So this one is the formula that's up here, that's on this page, n times n plus 1 times 2n plus 1 over 6. So if I apply that here, let's see, can I get them both in there? Maybe? Okay, so basically that is going to give me 20, right, because that's my first, times 21, and then 2 times 20 is 40 plus 1 is 41 over 6. And then my second formula then for k, that's the n times n plus 1 over 2 formula. So that would be 20 times 21 over 2. Okay. So we can add some of these up if we want to, right? So let me pull out my calculator here, or actually my handy dandy phone in this case, right? So let me just do the first calculation here. That would be 20 times 21 times 41, and then I'm going to divide that by 6. And so my first k squared 1 through 20, that's already a pretty big number, 2,870. Glad we didn't have to add those up one by one. And then over here I can simplify, this is 10, and then 10 times 21 is 210. So if I take my 2,870 and I add 210 to it, then I end up with 3,080. And I didn't have to do 1 squared plus 1, plus 2 squared plus 2, plus 3 squared plus 3, and so forth and so on. Okay? All right, so we have one more formula, and that is for if I have it cubed. Right? So if I have something cubed and I'm adding it over and over and over, then this is my formula for summation. So if I have k equals 1 and I go to 100, right, I definitely don't want to write those out over and over and over of k cubed. Then I can use my formula, right, I'll use this one here. So basically that would be 100 squared. And then times, I put in 100 plus 1, that's 101 squared, all over 4. So whatever that is, it's going to be a very large number. Let's see if I can get my calculator to work here for all of this. So we have 100 times 100, and since I just have my basic calculator app, I'm going to do times 101 times 101, and then I'm going to divide that whole thing by 4. So I end up with 25,502,500. Big number. It doesn't seem like it would get that big that fast, but it does, okay? So it's a nice quick way for us to sum things up, and it's a nice compact way for us to write a whole, right, if we wrote that out, like for all the hundreds, I mean, that would take like 3 lines, depending on how big your your handwriting is. I'd probably need the whole sheet of paper, okay? So this is just using our sigma notation. We're going to go forward using this.